Okay, here is the worked example for hypermetropia. So this is also the textbook example from page 123. And it says, a man with hypermetropia has an unaided near point of 50 centimeters and a far point of infinity. What is the power of lens needed to correct the hypermetropia, and what is his range of vision when he wears those lenses? So, hold on to your hats. He has hypermetropia, so that is to say he has long sight. And that means that he's good at long distances, but not at short distances. So his unaided near point is 50 centimeters, okay, as opposed to 25 centimeters. So hypermetropia is long sight. So we know that, let's sketch. Here is his eye. We know that he has an unaided near point at 50 centimeters. So let's put that out here. Now, we called that the actual near point before, but I'm going to call it the unaided near point here, and it's at 25 centimeters. So he can focus an object at 20, no, sorry, that was an error, wasn't it? It's 50. So he can focus an object at 50 centimeters. He can also focus a distant object, so his unaided far point is at infinity. Okay. Now, so he's okay at distance, but he's not okay close to. So we want to bring his near point closer in. In fact, we want to bring it into a normal near point. A corrected normal near point of 25 centimeters. Okay. To do that, then, because his eye lens is not able to properly converge rays from 25 centimeters, it can only do it if it's 50 centimeters away, so he needs a bit of help in the form of a converging lens. Okay. So he needs a converging lens, and the focal length of this lens is question mark. Okay, but what must happen is that the converging lens is going to converge rays of light so that they appear to come from his unaided near point, his actual near point. So in other words, if you've got a ray of light coming from the normal near point, the correcting lens can converge that a bit so that it appears to come from his unaided near point. Like that. And if the rays of light appear to come from his unaided near point, then his eye lens can deal with those and bring them to a focus at the back of the eye. Okay? So, in other words, if we put an object at the normal near point of 25 centimeters, in other words, we have an object distance of 25 centimeters, then that will produce a virtual image at 50 centimeters. So the image distance has to be 50 centimeters. And because the rays appear to come from that point but don't actually pass through it, it is a virtual image. Therefore, it has to be a negative. Okay, now that bit's tricky, so you might want to go back and look at that again. Okay, now, right, so we want to know the focal length for an object distance of 25 producing a virtual image at -50. So to do that, we use the lens equation. 1 over u plus 1 over v equals 1 over f. So in this case, we have 1 over plus 25 plus 1 over -50 is equal to 1 over f. No rearrangement is required, so we want to evaluate the left-hand side. Lowest common denominator has to be 50ths. 1/25th is 2/50ths, and -1/50th is -1/50th. 2 minus 1/50th is 1/50th. So 1 over f is 1/50th. Flip the guy, f is equal to positive 50 centimeters. Okay. Now I'm going to change color to work out the power. Right, okay, I'll put it here. So the focal length is plus 50 centimeters. Power is 1 over f. So in this case, that's 1 over 50 centimeters is half a meter, and it's positive 0.5 meters, and that gives us a power of positive 2.0 diopter. So the prescription that he needs is positive 2.0 diopter to correct his long sight. Okay. Now, what is the range of his vision when he wears these lenses? Well, what do we know? We know that without the lenses, his range of vision is from 50 centimeters to infinity. In other words, his unaided far point is at infinity, and his unaided near point is at 50 centimeters. Now, with the glasses, his normal near point, or his near point is brought in to a normal near point of 25 centimeters. What is then his far point? Is what we want to know. Okay. Well, let's see. If we sketch the lens again, the lens over here, here's the lens doing its job, and here's his eyeball. So, what about when he looks at something that's far away? Okay, well, what we know is that the eye lens can focus an object that is at infinity. So, yes. So in other words, the eye needs to receive rays which are parallel, okay, coming from an object at infinity, which is out here like this. Now, that means that the lens, the correcting lens, has got to produce parallel rays. Okay? In other words, it has to produce an image which is at infinity. The rays coming out of the lens must be parallel, therefore they must be coming from an image at infinity. So therefore, where is the object if that is the case? Well, where is there going to be a real object? I'm going to write that bit down first. So the spectacle lens must produce an image that is at infinity. And if the rays are coming from an image that is at infinity, they only appear to be coming from that image, so it's going to be virtual. Now, that must be a virtual image of a real object at some u, which is equal to question mark. Okay, well, if the lens is going to produce parallel rays, we can make a little shortcut here. Because we can say, if the lens is producing parallel rays, where must those rays have come from? And the answer is they must have come from the focal point. Okay. So there's the focal point. So if we have that u, the object distance, is don't know, but v has to be infinity, more strictly negative infinity since it's virtual. Well, in order to produce rays which are parallel, those rays must come from a real object which is at the focal point. In other words, u must be equal to the focal length. And the focal length of this lens, we already know, is 50 centimeters. Now, so therefore, what that means is that an object which is actually at 50 centimeters from the eye will produce parallel rays which the eye perceives as coming from infinity. Now, the eye can deal with those rays because it's hypermetropic. It can focus on an object at infinity. But that means that the furthest away an object can be from the eye is 50 centimeters. So a 50 centimeter object will appear as if it were at infinity. And therefore, the far point, the corrected far point, is only at 50 centimeters. So, therefore, the range of vision let's see, without and then with. It should be shown first. With lenses is, so we brought his near point in from 50 centimeters to 25 centimeters, is from 25 centimeters to, well, only 50. But the range without lenses, well, without the lenses, his near point was at 50 centimeters, but his far point was at infinity. So it's 50 centimeters to infinity. Now, what does that mean? Well, it means without the lenses, he's long-sighted. He can go from 50 to infinity with no problem, but inside 50 he's got a problem. So he can't read things close up. Therefore he needs the lenses. The lenses bring his near point into 25, so now he can do things nearby, but the lens has the effect of bringing his far point way in from infinity to just 50 centimeters. So now there's a big loss in distance vision with these glasses on. In other words, his range becomes 25 to 50. So what that means is that with these glasses on, he can focus on things close to, but not far away. So with spectacles or lenses, he can focus nearby objects. So for example, he could read a newspaper. But he can only focus out to 50 centimeters, so if he looked up from his newspaper, he wouldn't be able to focus things beyond that. So therefore, he's going to have to remove the glasses to recover his distance vision. In other words, to focus distant objects. And I guess that's why people who wear reading glasses, they may wear the reading glasses to read things, then to look up and look at objects further away. So for example, somebody who's giving a speech might need the glasses to read their notes, but if they want to look at the audience, they need to take the glasses off and then look at the audience, or possibly look over the glasses. So you might have seen people doing that. Okay, let's just review that one, because that was quite tricky. So this is the man with hypermetropia. That means he's got long sight. That means he needs a converging lens, because his eye lens is a little bit weak, not quite strong enough to do the job, so he needs a bit of help. Okay, without these glasses, he has an unaided near point of 50 centimeters, so he can't do close in, but he has an unaided far point of infinity. Now, he needs a converging lens to converge the light a little bit, so that an object placed at his normal near point of 25 centimeters produces a virtual image at his unaided near point, and then his eye lens can deal with that. So U is 25, V is negative 50, and when we put that through the lens formula, we come up with a focal length of plus 50 centimeters. So far, so good. The tricky bit then, I think, is working out the range of his vision when he wears these lenses. Well, without the lenses, uncorrected, his range is 50 to infinity. With the lenses, we've worked out that his new near point is 25 centimeters, which is where we want it. We want to know where his new far point has gone to. And we say that this is a converging lens. For him to be able to, if an object, a real object, is out here somewhere, for him to be able to focus that with his eye lens, the rays entering the lens must be parallel. In other words, there must be a virtual image produced by the spectacle lens at infinity. Now, in that case, where does the object have to be? Well, we say that if the image is at infinity, the rays are parallel, the emergent rays are parallel, and therefore the object must be placed at the focal point. And therefore the object distance is equal to the focal length, which is 50 centimeters. Now, if you don't believe that, you can use the ray or the lens equation to prove that, because we know what f is, we know that v is negative infinity, and we need to solve for u. Okay, So that means that his range with the lenses is from 25 only to 50. So the far point has been brought in from infinity to 50 centimeters. So the range is pretty constricted. The range without lenses was 50 to infinity. So this means that with the spectacles, he can focus successfully on nearby objects, so for example to read with, but because the range is so constricted, he must remove his glasses to focus on distant objects. Okay, now in the non-existent exams that we don't have to do, that is what we need to be able to do. We need to be able to describe these conditions, and we also need to be able to perform this kind of calculation on them. Let's go back to the learning intentions. Okay, right, magnification and power. Describe the use of lenses to correct myopia and hypermetropia. Well, we've used ray diagrams to describe how myopia occurs and how to correct it with a diverging lens, and hypermetropia, how it occurs and how to correct it with a converging lens. And we've done calculations, or we've done one of each, on the correction of long and short sight. One to correct short sight and one to correct long sight, including calculation of the new range of vision. Right, so the next and final step then is for you to have a go at exercise 2.3b, which is 4 questions performing these calculations on different people. So that's what you need to go and do next, and then to hand in your solutions to me. Okay. Right. That's the end of the lesson. I hope you enjoyed learning with me this afternoon. I've enjoyed learning with you.